Hello there, and welcome to the Sleepless Scientist, a calm corner of the universe where your thoughts can gently drift, and knowledge hums softly like a lullaby through the night. Tonight, we'll wander into a question so vast it seems to stretch beyond even the farthest galaxies. What is the ultimate boundary of the cosmos? Is there a point where understanding itself must stop? Before we set off, I'd truly appreciate it if you took a quiet moment to like this video and subscribe. Only if these slow journeys through science and wonder bring you a bit of peace. And when you're ready, feel free to leave a comment telling me where you're listening from and what time it is for you. It's always beautiful to imagine all of us, scattered across the world, yet sharing this same still moment in time. Now, dim the lights if you'd like. Let the soft hum of your surroundings fade into the background and allow yourself to unwind. Together, let's drift into the quiet edges of knowledge. And if your mind begins to wander, let it. That's part of the journey. The story will wait for you, unfolding softly in the dark. Imagine, for a moment, a civilization older than ours by millions of years. They have not only mastered fire, agriculture, and machines, but have climbed the rungs of the so-called Kardashev scale. They harvest the light of their star, then the power of their galaxy, building observatories not just the size of mountains or planets, but rings of mirrors circling suns and sensor webs stretched across clusters of stars. To them, knowledge is not a curiosity but a civilization-wide project. They wish to answer the deepest of questions. Are we alone? And can everything truly be known? It's an image almost dreamlike. Galaxy-spanning telescopes, ships wandering through the intergalactic night like lanterns set adrift on a sea. Yet even such titanic effort would eventually meet an edge. Horizons that no mirror can look past. Quantum mists no lens can penetrate. Limits that are written not in the frailty of biology or in the cost of technology, but in the very fabric of the universe itself. This is what we mean tonight by the ultimate cosmic limit. But before we get there, let's turn the story back to us. Tiny, restless creatures on a small blue planet, staring at the sky and asking the same kind of questions with far humbler tools. Because to understand limits, it helps to understand how far curiosity can carry us before we meet them. When you picture early humans watching the heavens, you might imagine not numbers and graphs, but campfires, stories, and careful observation. They noticed that the stars rose and fell in steady rhythms, that the moon had a cycle, that the return of certain constellations signaled the season of rains or of harvest. In those moments, knowledge was survival. Pattern finding was our first science. From there, we learned to predict, to anticipate, and to shape our lives around the cycles of nature. And yet even then, there must have been questions without answers. Why lightning cracks across the sky? Why the sun disappears in eclipse? Why some stars wander differently than others? Without tools, our ancestors filled the gaps with myth. Stories of gods, spirits, or cosmic animals made the world understandable, if not truly known. It was a kind of early lullaby for uncertainty, explanations comforting even if not precise. Centuries later, as civilizations grew, patterns of thought sharpened. Greek philosophers speculated about atoms, about infinity, about the nature of time. In China and India, astronomers tracked planetary cycles with meticulous care. The Islamic Golden Age brought algebra, lenses, and refined star charts. Each culture pushed against the unknown with the means it had, like waves slowly eroding a shoreline. The turning point, though, came with a man who raised a simple tube to the heavens. Galileo's telescope was barely more powerful than a modern pair of binoculars, and yet with it, he saw mountains on the moon, moons circling Jupiter, and phases of Venus that shattered the old, Earth-centered picture of the cosmos. What mattered was not the tube of glass and wood, but the principle behind it. Evidence rules. From Galileo onward, the thread of science was clear. Test the world, measure it, let reality answer. This method became humanity's ship of discovery, a fragile craft, patched with mathematics, reinforced with experiment, propelled by imagination. Each voyage gave us both answers and new limits. The microscope revealed cells, but then molecules asked new questions. The particle collider revealed quarks, but then the Planck scale loomed unreachable. The telescope revealed galaxies, but then dark energy and cosmic horizons mocked our reach. Always the horizon recedes. And so, the dream of that Kardashev civilization is in some sense our dream too, just stretched to mythic proportions. Could knowledge be complete, final, total? Could there be a day when every law is written down, every particle measured, every pattern revealed? Or is completeness itself an illusion, a word with no real referent, like chasing the edge of the rainbow? As you drift into these questions, let them wash over you gently. Tonight's story will move slowly from our humble beginnings to the towering ambitions of technology, and then into the walls, physical, logical, and infinite, that no civilization may ever cross. We will touch the edges of quantum mists, the event horizons of black holes, and the strange paradoxes of infinity, where probability itself dissolves. But here, in the beginning, it's enough to imagine the firelight of an ancient camp, the curiosity of the first stargazers, and the whisper that knowledge, though powerful, is never whole. Even civilizations that harness galaxies must eventually admit there are questions without answers, not because we lack imagination or perseverance, but because the universe itself has drawn a line. And so we begin quietly with the realization that the desire to know everything is perhaps the most human thing of all, and perhaps also the most impossible. When you close your eyes and imagine the very first humans gazing at the night sky, it is tempting to picture silence. But in truth, their minds must have been full of questions. Above them stretched a dome spattered with light, some of those lights fixed in careful arrangements, others drifting slowly across the heavens. They noticed that a cluster of bright stars rose only at certain times of year, and that their appearance was tied to the floods of a river, or the growth of crops, or the migration of animals. This noticing, this weaving of patterns, was the first kind of science. It was survival dressed as curiosity. A hunter could not afford to miss the shifting of seasons, nor a farmer the return of the rains. And so stories became calendars, and calendars became knowledge. When the Pleiades returned to the sky, it was time to prepare. When the moon swelled into fullness, tides followed. The sky was not only a mystery but a tool. To know it meant to live. At the same time, some questions pressed in from places that could not be answered so directly. Lightning split the sky and struck trees to flame. Eclipses turned day into sudden twilight. Comets swept in with long ghostly tails, frightening enough that whole kingdoms trembled at their appearance. With no instruments beyond the naked eye, our ancestors filled the gaps with stories of gods, spirits, and cosmic battles. It was not foolishness, but necessity, a way of taming the unknown so that sleep might still come at night. Explanations, even incomplete, soothed the imagination as lullabies do for restless children. Over centuries, certain minds began to push past story into structure. The Babylonians kept records of planetary positions so meticulous that modern astronomers can still use them. Greek philosophers proposed that the world was made of indivisible atoms, or that the Earth was a sphere suspended in space. Indian scholars debated infinity as a concept, and Chinese astronomers tracked the motion of the stars with patience that spanned dynasties. Across cultures, you see the same restless pattern. The human mind wanting not only to predict, but to explain. Yet explanation remained limited by tools. The eye, sharp as it may be, can only take us so far. For centuries, the stars were assumed to be fixed upon a crystalline sphere, carried in circles by perfect motions. It was elegant, but false. It took generations before the accumulated weight of observation cracked the old assumptions. The Islamic Golden Age offered lenses polished to precision, algebra that could describe patterns more cleanly than words, and star charts that mapped the heavens with increasing accuracy. European scholars rediscovered these ideas, translated them, and added their own. The slow layering of observation, mathematics, and philosophy created the foundation for something new. And then came Galileo, lifting a small telescope, more toy than triumph by modern standards, toward the heavens. Through it he saw that the moon was not smooth, but scarred with mountains and valleys. He saw that Jupiter was attended by 4 moons, spinning around it like dancers in a silent cosmic ballet. He saw that Venus had phases, like the moon, proving that it circled the sun. Each discovery was a gentle hammer striking cracks into the Earth-centered picture of the universe. What mattered was not only what Galileo saw, but how he insisted on believing his eyes over the weight of tradition. This was the quiet revolution. That truth must bend to evidence, not authority. That the universe could be read like a book, but only if one learned to listen to what was really there. Mathematics became the language, experiment the grammar, observation the ink. It was as if the world had been waiting, patient and immense, for us to learn how to ask it properly. From that moment, science was not only curiosity but method. A loop formed. Wonder sparked a question. The question led to an experiment. The experiment produced numbers. The numbers shaped theories, and theories returned to refine wonder again. It was like weaving, a shuttle moving back and forth across a loom, tightening the threads of knowledge into fabric. But fabric has edges. Even as telescopes revealed more stars, they also hinted at deeper mysteries. Galaxies rushing away from us, faster and faster, as if space itself were stretching. Even as microscopes revealed cells, they uncovered molecules, and within molecules, atoms, and within atoms, a strange zoo of particles that obeyed rules no common sense could predict. Each expansion of sight also revealed a new horizon, and so from the beginning, science carried both light and shadow, the power to illuminate and the quiet reminder that some corners may remain dark forever. Yet it was this balance that made it human, that gave it both humility and hope. Think again of that ancient campfire. Flames flicker, shadows dance on rock walls, and above stars glint through gaps in the smoke. One person tells a story of a god carrying the sun. Another whispers that perhaps the stars are fires of their own. Neither can prove it, but the act of wondering plants the seed of centuries. Out of questions that once frightened us grew the courage to look closer. And out of that courage, the path of science stretched onward, as it still does today. What began with patterns in the sky would become lightning captured in wires, invisible waves carrying voices across oceans, machines that peer into the body, and satellites that map galaxies beyond counting. Yet with each new triumph comes the whisper, there is always more. Beyond each horizon lies another. Beyond each answer, a question waits. As you listen, let that be the gentle rhythm, knowledge expanding like ripples in water, never reaching an end, only carrying curiosity further outward. The night sky above us is no longer just a ceiling of lights, it is a canvas of questions. And as we drift deeper into tonight's journey, we will follow those ripples into the tools and ambitions that carried us from the campfire to the cosmos. On a summer night long ago, before the invention of electricity, before cities glowed with their false dawn of light, a storm would have been one of the most fearsome spectacles the sky could offer. A sudden flash, a jagged tear of white fire splitting the heavens and striking the earth with a crack so loud it seemed the world itself had broken open. To the people who lived then, lightning was not a question of voltage or charge. It was a divine weapon, a message from gods, a reminder of power beyond human reach. And yet, even in the fear, there was curiosity. What was this fire that fell from the sky? Why did it strike sometimes but not always? Could it ever be understood or even tamed? Centuries later, a man named Benjamin Franklin decided to find out in the simplest, most reckless way imaginable. He flew a kite into a storm. From that dangerous curiosity came the first hints that lightning was not divine wrath, but electricity. A spark jumping to a key tied on a string was crude evidence, but evidence nonetheless that lightning and the small shocks known from rubbed amber were one and the same. A thread had been pulled, and once pulled, it unravelled further and further. Electricity, once feared, became a subject of careful study. Scientists such as Coulomb began to measure how charges attract and repel. Volta built batteries, turning fleeting sparks into steady currents. Faraday discovered that moving a magnet could create electricity, and that electricity could in turn create motion. These were not isolated tricks, but parts of a larger tapestry. And then came James Clerk Maxwell, who wove the threads together into a set of equations, 4 elegant lines that captured the behaviour of electricity and magnetism, not as separate mysteries but as facets of a single, unified force, electromagnetism. What began as fear of lightning had transformed into laws of nature, so precise that they could predict the path of a radio wave across the world or the rainbow colours splitting through glass. The same force that cracked open trees in a storm also carried voices along telegraph wires, lit lamps in distant towns, and eventually allowed signals to leap invisibly through the air as radio, as television, as the Wi-Fi connecting us now. The chain from lightning to electromagnetism to modern physics is not a straight ladder of discovery, but more like threads woven again and again into the fabric of knowledge. Each new experiment became a strand, each new theory a way of binding them tighter. And even as the tapestry grew more intricate, new patterns emerged. When Maxwell's equations were studied closely, they revealed that light itself was an electromagnetic wave. Suddenly, vision and electricity, 2 seemingly unrelated phenomena, were joined. Later, as physicists probed deeper into the atom, they realized that the electromagnetic force was responsible not only for lightning and light, but for the very structure of matter, binding electrons to nuclei, holding chemistry together, making life itself possible. What began as terror in a storm had revealed itself as one of the 4 fundamental forces shaping the universe. This, perhaps, is the deepest rhythm of science. Curiosity leads to experiment, experiment to theory, theory to new curiosity. Each part reinforces the other, as if reality can only be persuaded to give up its secrets when approached from 3 directions at once. Experiment alone gives numbers, but without theory they remain mute. Theory alone spins castles in the air, but without experiment they crumble. Mathematics alone is a symphony unheard, until it finds a place to resonate with the world. Together they weave something lasting, and yet this weaving is never final. The moment we declare knowledge complete, the fabric frays at the edges. Lightning revealed electricity, electricity revealed magnetism, magnetism revealed light, and light itself revealed the deeper puzzles of relativity and quantum mechanics. Maxwell's equations, perfect though they seemed, did not explain why atoms are stable, or why light behaves both as a wave and a particle. Each discovery, no matter how elegant, eventually leads us to the edge of a new unknown. But there is something comforting in that. To know that lightning, once a terrifying rift in the sky, became the doorway to understanding forces that shape everything from galaxies to neurons. To know that one question can spark centuries of insight, and that insight can build machines, instruments, and tools that extend our reach further still. Each strand of knowledge is not isolated, but part of a living weave, growing denser, more colourful, more astonishing with time. Perhaps this is why the metaphor of science as a ladder feels too rigid. not too linear. A ladder suggests a single path upward, one rung after another, towards some final platform of truth. But in truth, science is more like a tapestry or a garden. Threads cross and recross, unexpected connections appear, and what was once a small seed of curiosity grows into a tree shading entire landscapes of thought. Lightning, frightening and mysterious, seeded not only physics but technology, medicine, communication, and the very infrastructure of modern life. And as with any fabric, the beauty lies not only in the central pattern, but also in the borders where threads begin and end. Science's borders are not failures but invitations, the places where curiosity pulls at the next loose strand. When Franklin asked if lightning could be tamed, he could not have imagined wireless networks or MRI scans, yet they were all waiting in the weave. Tonight, as we drift through this story, let the chain of lightning remind us that every question, no matter how wild, may hold within it the beginning of entire worlds of knowledge. And yet, as rich as the tapestry becomes, there will always be threads we cannot follow to their end. That is not a flaw, but a promise, that curiosity will always have a place to wander, and wonder will never be exhausted. For most of human history, the eye was our only true instrument. A miracle of biology, yes, able to take in the shimmer of stars, the detail of leaves, the subtle flicker of expressions across a face. But as powerful as vision is, it is bounded. The stars looked like points because they were too far. The cells of our body were invisible because they were too small. The slow movements of planets were measurable, but only with great patience. The eye gave us patterns, but it withheld the hidden worlds beyond them. Then came the tools that stretched our sight. Glass, once a simple luxury shaped into beads and vessels, was polished into lenses, and lenses became windows into scales of the universe we had never seen. With a telescope, Galileo watched mountains on the moon and moons around Jupiter. With a microscope, Van Leeuwenhoek saw what he called animalcules, tiny creatures swimming in a drop of water, alive, complex, previously unimaginable. It is difficult even now to grasp the sheer shock of those first glimpses, to look at the heavens and realize the earth is not the center, to peer into water and realize it is teeming with invisible life. Each tool was not only a device, but a revelation. Over centuries, telescopes grew larger, perched on mountaintops where the air was thin, then lofted into space where Earth's atmosphere no longer blurred the view. The Hubble Space Telescope gave us visions of galaxies so far away that their light began its journey before our species even existed. Hubble's deep field images, little more than long exposures pointed at dark patches of sky, revealed that darkness itself was crowded with galaxies, each containing billions of stars. To see those faint smudges was to stretch the human imagination as far as our instruments could reach, and still, we were not done. Telescopes moved beyond visible light into radio waves, X-rays, and infrared. The James Webb Space Telescope, orbiting far from Earth, now peers into the universe's earliest moments, its golden mirrors tuned to infrared light that can slip through cosmic dust. Each wavelength tells a different story. Radio telescopes catch the whisper of hydrogen clouds, X-rays reveal violent black hole jets, infrared shows baby stars cocooned in nebulae. The universe was never a single picture, but a layered tapestry, waiting for us to tune our instruments to its many voices. While telescopes opened the heavens, microscopes opened the hidden universe within us. At first, they showed cells, simple and miraculous. Later, improved lenses revealed the nuclei inside those cells, then the twisted spirals of DNA, then the precise dance of proteins folding and unfolding in the machinery of life. What the naked eye saw as a simple drop of pond water, the microscope revealed as a world as rich and varied as forests or oceans. The small was not simple, it was vast. But seeing is not only about magnifying. As our instruments gathered more and more detail, they also gathered more data than the mind could hold. Telescopes returned oceans of starlight. Microscopes produced libraries of slides. Laboratories generated streams of numbers. To make sense of all this, another tool arose. Not glass, but logic made mechanical. Computation. At first, computers were slow, room-sized machines crunching equations for wartime ballistics or census counts. But soon, they became companions of science. They simulated atoms colliding, stars forming, galaxies swirling. They took the raw signals from telescopes and assembled them into images that humans could actually see. They sifted through genetic code, hunting for patterns in the four-letter alphabet of DNA. Computation became not just a tool for handling data, but a new way of seeing. Where the eye failed, and even the lens failed, the algorithm succeeded. Together, telescope, microscope, and computation formed a triad of extended vision. One stretched outward into the cosmos, one inward into the cell, one across patterns too vast or subtle for unaided minds. They were lanterns hung in the dark, each casting a circle of light. But with every circle of light, the surrounding shadows also deepened. To see galaxies in the deep field was to realize how much more lay beyond. To see DNA was to realize how much complexity remains unexplained in its folds. To run simulations was to realize how dependent knowledge had become on assumptions built into code. Perhaps this is why science has never been only about tools, but about the humility to recognize their limits. A telescope shows the universe as it looks through glass. A microscope shows life as it appears under light. A computer shows reality as filtered by models. Each lantern illuminates, but each has blind spots. Still, without them, we would remain in the small circle granted to us by biology alone. Think of the night sky again, but this time imagine it as seen through three eyes. The naked eye seeing bright stars and familiar constellations, the telescope eye revealing galaxies swirling beyond, and the computational eye layering maps, distances and simulations until the sky becomes a three-dimensional atlas. Knowledge is no longer only what is visible but what can be modelled, magnified and translated. These tools did more than extend vision, they extended imagination. Once we saw moons around Jupiter, we could imagine worlds beyond Earth. Once we saw bacteria, we could imagine diseases caused by them and cures that might follow. Once we processed data from the cosmic microwave background, we could imagine the birth of the universe itself. In stretching our eyes, these tools stretched our minds, and yet the lantern metaphor remains. Each tool, no matter how powerful, casts light in some directions and leaves others in shadow. The telescope cannot see inside a cell. The microscope cannot see the edge of the universe. The computer cannot show us what lies beyond the assumptions of our models. Knowledge expands, but the darkness does not shrink. It simply rearranges itself, waiting beyond the glow. As we drift further into tonight's journey, let that be a quiet comfort. The tools we have built have given us wonders our ancestors could never dream of, yet they remind us gently that seeing everything is impossible. There will always be shadows, and in those shadows lies the next question, the next curiosity, the next reason to look again. If the telescope, the microscope, and the computer were lanterns in the dark, then what might the lanterns of tomorrow look like? Each generation has stretched its vision further, and it is tempting to imagine that the next step will be simply more of the same. Bigger telescopes, stronger microscopes, faster computers. But sometimes the greatest leaps come not from making tools larger, but from turning the universe itself into a tool. One such dream is the solar gravitational lens. Our sun, massive and round, bends light as it passes near its edge. This bending is not just a small effect. It can, in principle, focus light from distant objects like a cosmic magnifying glass. If a spacecraft were placed in just the right spot, about 550 astronomical units from the Sun, far beyond Pluto, it could use the Sun's mass as a lens, producing images of distant planets with astonishing resolution. Not just dots of light, but continents, clouds, even oceans on worlds orbiting other stars. To think that the Sun itself could become part of a telescope is a reminder that sometimes the universe provides instruments already built, waiting for us to use them. Other visions are grander still. Imagine not one telescope but thousands, spread across moons and planets, linked together by beams of light into a single, enormous array. The wider the separation, the sharper the vision. So in theory, a telescope network spread across the solar system could resolve details at unimaginable scales. We already link radio dishes across continents, combining signals to produce images sharper than any single dish could achieve. Tomorrow, perhaps the very architecture of the solar system could become an observatory. Some proposals stretch even further to structures that sound like myths. Dyson spheres, for instance, are imagined swarms of satellites surrounding a star capturing its light. While usually pictured as energy collectors, they could also function as an observational network. Thousands of instruments linked by streams of light, building a picture of the cosmos in more detail than any solitary device could manage. We are far from such feats, but to imagine them is to sense the scale of curiosity itself. And yet, for all the grandeur of these possibilities, each carries the same gentle warning. Every tool, no matter how ambitious, meets a horizon. Even if we use the Sun as a lens, even if we scattered telescopes across planets, even if we captured the light of a star, we would still be confined by the boundaries of the observable universe. The cosmos is not infinite to our eyes. It is wrapped by the light that has had time to reach us, and beyond that there will always be a veil no lens can pierce. There are also softer limits, the kind that creep in through the cracks of reality. The further we push our instruments, the more they must contend with noise, quantum jitter, thermal fluctuations, cosmic rays that strike detectors at random. Even in the cleanest design, uncertainty whispers. The fabric of the universe itself is not smooth but restless, and instruments cannot erase that restlessness. They can only measure it, and then pause at the edge of what can be known. This does not make the dream futile. In truth, it makes it more precious. To imagine a solar gravitational lens is to remember that we are still children at the shoreline of a vast ocean, holding up our glass bottles to catch whatever waves we can. Each new instrument is like another bottle, filled with a little more starlight, a little more memory of what lies beyond. We may never hold the entire sea, but what we capture is still enough to change our world. Think of how the Hubble telescope reshaped our sense of the cosmos with a single image. The deep field, where a tiny patch of sky revealed thousands of galaxies. Now imagine a future instrument revealing the continents of a planet orbiting a star light years away. It would not answer every question, but it would give us something astonishing. The knowledge that worlds like ours are not rare, that life may be waiting, that we are not isolated but part of a wider story. Sometimes a single image is enough to turn philosophy into certainty. Perhaps this is the deeper role of the super instruments, not to complete knowledge, but to widen it, to give us new vantage points, new questions, new humility. They are steps in a dance with the unknown, each one reaching further into the dark, only to reveal that the dark stretches further still. As you drift with this thought, imagine the night sky again. Now, instead of constellations drawn by myth, imagine constellations of instruments, satellites in arcs around planets, mirrors stretched across orbits, lenses made of stars themselves. Picture a civilization that weaves its technology directly into the fabric of the cosmos, turning space into one vast observatory. It is both awe-inspiring and strangely quiet, like lanterns hung along the edges of an endless sea. And remember, every lantern leaves shadows, the dream of seeing everything as beautiful, but the horizon will always remain. What matters perhaps is not reaching the end, but extending the circle of light a little further each time and finding wonder in what is revealed there. When you think of fire, you might picture something small. Flames licking at logs, the glow of a hearth, the comfort of warmth against a cold night. For early humans, this was the very definition of power. The ability to hold fire, to cook food, to push back the dark. Over centuries, our fires grew larger. They became the engines of steamships, the furnaces of cities, the beating hearts of factories. Energy, in every age, has been the hidden companion of knowledge. The more we wanted to know and do, the more fire we needed to borrow from the world. It is with this in mind that scientists once proposed a thought experiment called the Kardashev scale. Instead of measuring civilizations by wealth or population, it asked, how much energy do they command? A Type 1 civilization would use all the power available on a single planet. Winds, rivers, oceans, the warmth of its star as it falls to the ground. A Type 2 would go further, capturing the full radiance of its star. And a Type 3, almost mythical, would command the energy of an entire galaxy. We, for all our cities and lights, are not even Type 1. We use a fraction of the Earth's available power. But the idea of climbing the scale has always stirred the imagination, because with greater energy comes the possibility of greater knowledge. To study distant galaxies, to transmit data across interstellar distances, to build machines vast enough to probe the smallest corners of physics, all of these require power at scales beyond our current grasp. Curiosity is a fire, and fire must be fed. When people speak of a Type 2 civilization, they often invoke the image of a Dyson sphere. At first glance, it sounds like science fiction, an enormous hollow shell completely surrounding a star, capturing every photon. But such a rigid sphere is almost certainly impossible. Instead, the more realistic idea is a swarm of collectors, millions of satellites orbiting a star, each harvesting a fraction of its light and beaming it where it is needed. Not a shell, but a cloud, shimmering like dust motes around a lamp. If such a swarm were ever built, the star would grow dim from the outside, its light intercepted before reaching the cosmos. To distant observers, it might appear not as a blazing sun, but as a faint glow of waste heat, a kind of quiet signature of intelligence. Astronomers have even searched for such signatures in the skies, scanning for stars whose light seems curiously muted. So far, none have been found, but the idea lingers. Perhaps somewhere, hidden among the billions of stars, a civilization has already woven such a net of collectors, turning their star into both a battery and a beacon. The reason for such ambition lies not only in survival, but in the hunger for knowledge. To store the data of billions of observations, to process them, to simulate realities in search of patterns, each of these is an act of energy as much as of intellect. Already, our own computers consume vast amounts of electricity, data centers glowing like silent furnaces in the night. Imagine scaling this upward to the level of entire star systems. The more a civilization knows, the more energy it must wield to continue knowing. Knowledge is not free, it is paid for in watts. Beyond stars lies the vision of galaxies themselves as sources of energy. A Type 3 civilization, if it could exist, would gather the output of billions of suns. The scale is almost impossible to picture. Galaxies are not small, neat disks, but sprawling cities of stars, tens of thousands of light years across. To harness such energy would mean spreading across vast distances, weaving machines into the very architecture of the cosmos. Whether such a thing is possible is unknown, but to imagine it is to glimpse the upper bounds of ambition. And yet, ambition does not erase limits. Even Dyson-like swarms cannot capture light without cost. Materials would have to be mined from planets, moons, perhaps dismantled asteroids. Whole worlds might be stripped bare to build such constructs. To pursue knowledge at such a scale would reshape the environment in ways we cannot fully picture. Perhaps that is why, even in theory, there is always a note of humility. Every star harnessed is also a star dimmed. Every planet dismantled is also a home lost. The fire of curiosity is bright, but it leaves ashes behind. Still, the thought experiment is valuable. It reminds us that every step we take in pursuit of knowledge rests on an invisible foundation of energy. When we point telescopes into the night sky, when we run particle accelerators, when we simulate the early universe, we're not just asking questions, we are burning firewood at the hearth of reality. For us, the logs are fossil fuels, nuclear reactors, solar panels. For others, perhaps, the logs are stars themselves. Think of a candle on a table. Its flame flickers, small but steady, illuminating the room. Now imagine that same principle extended, first to the fires of cities, then to the power of planets, then to the brilliance of stars. The difference is only of scale, but the pattern is the same. Curiosity demanding light, and light demanding energy. As you rest with this image, remember that even as we imagine Dyson's swarms and galaxy-spanning networks, we ourselves still sit around a much smaller fire. Our energy comes with limits, and those limits shape the questions we can ask. Perhaps that is why we dream of harnessing stars, not only for survival, but for the chance to keep asking questions without end. For as long as there is power to feed it, curiosity remains awake. Imagine holding a clock in your hand. You can open the back, look at the gears, see how they mesh together to turn the hands across the face. If you want to understand the clock, you don't have to break it, you just need to watch it work. But the universe is not so kind. Its workings are hidden not in gears, but in particles smaller than atoms, particles that do not show themselves unless pushed, prodded, or collided at tremendous energies. To study reality at its deepest scales, we do not open the clock gently. We smash it and watch the pieces fly. This is the principle of the particle collider, one of humanity's most audacious tools. At first glance it seems simple. Accelerate particles, protons, electrons, heavy ions, close to the speed of light, then steer them into head-on collisions. The impact tears open the substructure of matter, releasing showers of new particles that detectors capture like intricate cameras. Out of the debris, patterns emerge. Out of those patterns, laws are written. Early experiments began humbly. Cathode ray tubes, designed for displays, were also little particle guns, accelerating electrons across glass. Later, cyclotrons spun particles in magnetic circles, making them faster and faster until they smashed into targets. Each increase in energy was like turning up the zoom of a microscope, letting scientists peer into smaller and smaller distances. This effort culminated in the construction of the Large Hadron Collider, LHC, near Geneva, a ring 17 miles in circumference buried underground where protons are accelerated to energies of several tera electron volts before colliding. The LHC is not only a machine, but a landscape, vast tunnels curving through rock, detectors the size of cathedrals, thousands of scientists watching over screens like astronomers once watched the sky. It was here that the Higgs boson was confirmed, a particle long predicted, the final piece of the Standard Model puzzle. With it, we understood why particles have mass, why matter exists in stable form. It was a triumph, celebrated worldwide. The Standard Model of particle physics has been one of humanity's most successful intellectual achievements. It describes quarks, leptons, bosons, the basic ingredients of matter and force. It explains electromagnetism, the weak and strong nuclear forces, and most of the everyday universe. Predictions made by its equations have been confirmed again and again, often to extraordinary precision. To many it feels complete, like a well-built house with every brick in place. And yet, the house has cracks. Gravity is missing from the model. Dark matter, which outweighs visible matter 5 to 1, is invisible to it. Dark energy, which accelerates cosmic expansion, is entirely unaccounted for. Even neutrinos, ghost-like particles streaming through every square centimetre of your body by the trillions each second, do not fit neatly into the theory. The standard model is not wrong, it is simply incomplete, a map that ends just before the most interesting terrain. To reach beyond it, colliders must grow. The logic is straightforward. To probe smaller scales, you need higher energies. To see into the structure of matter at the tiniest distances, you must crash particles together at velocities so extreme that they briefly create conditions like those just after the Big Bang. The problem is scale. The energies required to reach the Planck regime, where quantum mechanics and gravity intertwine, are unimaginably high, trillions of times beyond what the LHC can achieve. To build a collider capable of such feats would require not a ring beneath a single city, but perhaps one circling a planet. This paradox is quietly poetic. To learn about the smallest structures in the universe, we must build the largest machines. The search for the tiniest requires monuments at cosmic scale. It is as if nature has hidden its secrets behind a wall that only giants can climb. But colliders are more than brute force. They are also triumphs of subtlety. Detectors at the LHC are layered like onions, designed to catch every fragment of a collision. Some sensors measure the paths of charged particles bending in magnetic fields. Others catch bursts of energy left by photons or jets. Computers record and sift through the data, filtering millions of collisions per second, keeping only those most likely to matter. The result is not chaos, but a portrait, a pattern drawn from fragments of debris. To the trained eye, it is as elegant as any painting. And so colliders remind us of both ambition and humility. Ambition, because we have built machines that stretch the imagination, flinging protons around a ring at 99.9999999% of the speed of light. Humility, because even these machines fall short of the ultimate goal. We have mapped quarks, but the deep fabric of space-time still lies beyond reach. Each collider feels less like the final answer and more like a rung on an endless ladder, or perhaps more gently, another thread woven into the tapestry of knowing. There is also the quiet question of limits. How much larger can we build? How much energy can we channel without drowning in cost or risk? Perhaps there will come a time when colliders as we know them give way to new methods, plasma accelerators, laser-driven beams, even cosmic rays harnessed as natural laboratories. But for now, colliders remain our most daring attempt to make the invisible visible, to ask the universe to reveal its gears by breaking them open for us. As you listen, think of it this way. Each time a collision occurs, a tiny flash of energy blazes brighter than anything the particles have ever known in their long cosmic journeys. Out of that flash comes a whisper of reality's hidden language. It may not tell us everything, but it tells us something. And sometimes, something is enough to light the path to the next question. When most people hear the phrase black hole, they imagine something that devours, a darkness so complete that nothing, not even light, escapes its grasp. It feels less like a machine and more like a monster lurking in the cosmos. And yet, physicists have long wondered if black holes, rather than being only ends, might also be beginnings, if, instead of pure destruction, they might serve as the ultimate engines. The idea comes from how black holes interact with the space around them. A black hole is not simply an empty pit. It is an object defined by mass, spin and charge, curving space-time into a funnel so steep that matter and energy fall inward. But just outside the event horizon, especially for spinning black holes, there are regions where strange things can happen. One of these is called the ergosphere, a zone where space itself is dragged along by the hole's rotation faster than any object could resist. In that zone, it is possible, at least in theory, to drop in matter in just the right way and extract energy from the hole's spin. This concept, called the Penrose process, was one of the first hints that black holes could, paradoxically, give as well as take. Later, other proposals followed. The idea of a black hole bomb imagined surrounding a spinning hole with a mirror, causing trapped light to bounce again and again, stealing energy from rotation until it bursts outward in a flood. More conservatively, astrophysicists have studied accretion disks, the hot, whirling disks of gas that form as matter falls into black holes. These disks, heated to extraordinary temperatures, can radiate more efficiently than stars, converting mass into energy with startling effectiveness. Already in nature, black holes power quasars, distant cosmic lighthouses shining brighter than entire galaxies. To harness such a source would be to tap into one of the most efficient energy systems the universe allows. And then there is the whisper of something stranger still: Hawking radiation, the faint emission predicted by quantum theory at the edge of a horizon. In principle, a small black hole could evaporate over time, releasing energy as it does. To control such a process would be to hold a furnace whose fuel is space-time itself. Why does this matter to the story of knowledge? Because energy and knowledge are bound together. To process information, to store it, to build machines vast enough to simulate universes or power observatories at the edge of light, requires fuel. The dreams of black hole engines are dreams of matching the cosmos with equal force, of giving curiosity the power it craves to never run out of questions. For some thinkers, the ultimate computer might even be powered by a black hole, its computations etched into the very fabric of space-time, its memory banks as deep as gravity wells. But like all dreams, this one carries shadows. To approach a black hole is to dance on the edge of catastrophe. Radiation, tidal forces, and sheer distances make engineering nearly impossible. A civilization capable of harnessing such power would be almost unrecognizable to us, spread across star systems, patient enough to plan projects lasting millennia. Even then, success might remain out of reach. And beyond the physical challenge lies the philosophical one. If a civilization dismantles worlds to build Dyson swarms, what would it mean to tether a black hole as a power plant? What price would be paid for such ambition? Energy in such abundance might bring knowledge, but it might also tempt domination, excess, or ruin. Some limits are not physical but ethical, shaped by the recognition that not everything possible is worth doing. Still, it is hard not to be awed by the vision. Picture a civilization orbiting a black hole, not in fear but in purpose. Vast collectors hang in the void, catching radiation from the accretion disk. Machines skim the edge of the ergosphere, siphoning rotation. Data centers the size of moons hum with power drawn from the most mysterious objects in existence. Around them, the black hole itself sits silently, a dark sun feeding the hunger for knowledge. And yet, perhaps the most important reminder is this: even black holes, those symbols of extremes, cannot break the final limits of knowing. They offer energy, yes, but not infinity. Their horizons hide information forever. Their cores, if they exist in any describable form, remain beyond reach. They're both gift and gate, generous with power, stingy with truth. As you drift with this thought, let it settle like a paradoxical lullaby. The most powerful engines in the universe are also the most secretive vaults. They tempt us with unimaginable energy, but they also remind us that some doors will never be opened. Knowledge may grow, but it will always carry shadows. Ambition may burn, but it will always meet a horizon. And perhaps that is why black holes fascinate us, not only because of what they give or take, but because they embody in their silence the very balance between possibility and limit. When you look up at the night sky, the stars seem close together, like grains of salt scattered on black cloth. The constellations form neat shapes, as if you could trace them with a finger and reach from one star to the next. But this is an illusion born of distance. The nearest star to our Sun, Proxima Centauri, is more than 4 light-years away. In kilometres, that is a number so large, over 40 trillion, that the mind cannot hold it. To give it shape, imagine driving to Proxima at highway speed, say 100 kilometres per hour. You would arrive in about 50 million years. The stars are not neighbours, they are islands, each one separated by gulfs larger than any ocean on Earth. This, more than any other fact, is what makes interstellar travel so difficult. The physics of propulsion, the engineering of ships, the ingenuity of design, all of these matter. But what they must confront is not a technical problem alone. It is distance itself, stretched to a scale where human lives and human patience falter. One answer that thinkers have offered is the world ship, sometimes called a generation ship. In this vision, a spacecraft is not a vehicle in the ordinary sense, but a moving home. Entire communities live inside with fields for crops, habitats for families, and systems to recycle air and water across centuries. The ship travels slowly, perhaps at a few percent of the speed of light, and by the time it reaches its destination, many generations will have been born, lived, and died within its walls. The original travellers would never see the new star. Their great-grandchildren, or perhaps even further descendants, would be the ones to step out beneath a new sun. The idea is haunting. It suggests not exploration as we know it, but migration in deep time. A society folded inside a shell of metal, adrift for centuries, carrying not only its biology but its culture, its songs, its disagreements, its quiet nights. In some sense, a world ship would not be a journey to another star, but the creation of a new civilization entirely, one defined by the journey itself. The ship would be both ark and tomb, a place where the meaning of home shifts with every passing generation. Another possibility is more biological: torpor or suspended animation. Instead of generations living aboard, perhaps travellers could sleep through the centuries, their bodies cooled, their metabolism slowed, their cells protected against decay. In fiction, this appears often as cryogenic sleep. In reality, scientists study hibernating animals like bears or squirrels, searching for mechanisms that could be applied to humans. If perfected, it would allow a crew to leave Earth, close their eyes, and awaken not to their children's children's children, but to the light of a new sun. It would turn centuries into the blink of a dream. And then there are the opposite visions, the ultralight and fast. Instead of building giant habitats or coaxing biology into centuries of slumber. What if we stripped travel down to the smallest possible probes and flung them outward at a fraction of light speed? This is the hope of light sails, ultra-thin sheets pushed by powerful lasers carrying miniature instruments. A gram-scale probe no bigger than a smartphone could in theory be accelerated to 20% of light speed, reaching Proxima in a few decades rather than millennia. It would not carry humans, but it could carry eyes and ears, tiny cameras and transmitters, sending back images of alien worlds. Light sails embody a different philosophy, that the first explorers may not be us, but our tools. Humans are heavy, fragile and impatient. Instruments, by contrast, are small, resilient and tireless. Perhaps the first photographs of another Earth-like planet will be taken not by a crew stepping onto soil, but by a probe no larger than your hand, sailing through the dark on a beam of light. Yet every approach faces its own limits. World ships demand resources beyond anything we have yet built. Torpor remains beyond current biology. Light sails require lasers of staggering power and precise aiming across light years. And all must confront the scale of distance itself. A journey of 4 light years at 20% of light speed still takes 20 years one way. plus 4 more for the signal to return. To the universe, that is a blink. To human lives, it is a span of waiting that requires patience bordering on devotion. There is something quietly humbling in this. The galaxy invites us with its countless suns, yet it sets the price of entry in time and distance. We can dream of ships, sails, or sleep, but each dream is tempered by the same reality. The stars are far. Not impossibly far, perhaps, but far enough that any crossing will be unlike anything humanity has ever attempted. Think of a message in a bottle. On Earth, we might throw such a bottle into the sea, watching it drift until currents carry it to another shore. It may take months or years. You may never see it again. Interstellar travel, in a sense, is like that. We hurl our bottles, whether ships, probes, or frozen passengers, into the cosmic ocean and wait to see if they arrive. The ocean, however, is vast beyond measure, and the shores are hidden by distance and time. Still, we try. We imagine. We design. Because curiosity is not silenced by difficulty. Even if the stars are unreachable for now, the thought of reaching them draws us forward, just as early sailors were drawn by horizons they could not yet cross. Perhaps, someday, the gulfs will be bridged, not easily, not quickly, but with the patience of centuries. Until then, the night sky remains both map and mystery, a reminder that the universe is not small, and that knowing it requires not only ingenuity, but endurance. If light sails and world ships are dreams of delicacy and patience, then nuclear propulsion is a dream of raw force. It imagines not drifting on currents, nor sleeping through centuries, but lighting one explosion after another and riding the shock waves into the dark. The idea seems reckless at first, almost absurd. Use nuclear bombs, weapons of destruction, to propel a ship to the stars. And yet, for a time in the mid-20th century, this idea was not only considered, but studied seriously, under the name Project Orion. The principle was simple in outline, if terrifying in practice. A ship would carry a massive plate at its back, cushioned by shock absorbers. Small nuclear devices would be ejected and detonated just behind the plate. Each blast would slam into the ship, kicking it forward, and the shock absorbers would smooth out the violent push into steady acceleration. Repeated hundreds or thousands of times, the blasts could in theory push the ship to a significant fraction of light speed. Here, nuclear fire would not destroy a city, but lift a crew toward the stars. Orion was not fantasy. Designs were drawn. Scaled-down tests with conventional explosives were performed. The mathematics worked. The engineers believed it could be done. What ended the project was not physics, but politics. The Partial Test Ban Treaty of 1963 outlawed nuclear explosions in space, and the prospect of filling the heavens with radioactive fallout was enough to halt the idea. Still, Orion remains a haunting image of what could have been. A world where the atomic age reached outward, not just inward. Beyond bombs lay subtler hopes. If fission was not enough, perhaps fusion could carry us further. Fusion is the process that powers stars, the merging of light nuclei into heavier ones, releasing vast amounts of energy. If bottled and controlled, it could provide a far more efficient drive than fission. Concepts like inertial confinement, pellets of fuel crushed by lasers or magnetic pulses, and magnetic confinement in tokamaks were considered as possible ways to build fusion engines. A ship powered by fusion could, in principle, cruise between stars at significant speeds without the thunderous violence of nuclear detonations. Some designs imagine pulsed fusion, where pellets of fuel are ignited one after another behind a spacecraft, creating controlled bursts of thrust. Others envisioned magnetic nozzles channeling the plasma from fusion reactions into directed exhaust. Each scheme had its elegance, and each shared the same problem. Fusion, even today, remains beyond our steady mastery. We have coaxed it to burn for moments in laboratories, but not yet tamed it into a sustained practical source of power, much less one compact and reliable enough to fit aboard a starship. Still, these nuclear dreams illustrate something deeper. They reveal how the desire to travel collides with the arithmetic of energy. The closer you want to come to the speed of light, the more your energy demands explode. Doubling your speed does not simply double the cost, it multiplies it many times over. At high fractions of light speed, the energy required to push even a small ship begins to rival the total output of entire civilizations. This steep curve is not unique to spaceflight. It is the same in many corners of life. The first steps are easy, the next harder, and the last stretch, the final approach to perfection, becomes almost impossible. You can feel it in running a race, where the first strides come lightly, but the sprint at the finish drains everything. You can feel it in trying to balance a pencil on its tip, where stability comes easily at first, but becomes fragile as you reach for precision. The physics of relativity is built on the same principle. As a ship nears light speed, its mass effectively increases, resisting further acceleration, and the required energy rises toward infinity. That is why nuclear propulsion feels like a bridge between two worlds. It is a dream that acknowledges the enormity of the problem and still dares to leap. It says, we cannot drift to the stars, not in any time frame that feels human, but perhaps we can burn our way there. Whether through bombs or bottled stars, the nuclear path embodies urgency, as if the stars are not just an invitation, but a challenge we're compelled to meet with fire. And yet, the challenges remain immense. Carrying the fuel alone becomes daunting. A ship must haul not only its payload, but the energy to accelerate it. And the more fuel you carry, the heavier you are, and the more fuel you need in turn. It is a spiral of burden, one that nuclear propulsion only partly softens. To reach even 10% of light speed with a sizable crewed vessel would require energies equivalent to detonating millions of nuclear devices. The scale strains not only technology, but imagination. So perhaps nuclear dreams are best seen as stepping stones. They may not carry us all the way to the stars, but they mark a stage in our thinking, a recognition that the challenge is not only distance but energy itself. In their boldness, they remind us that exploration has always been tied to risk and audacity. The first ships that crossed oceans were not safe, nor were the first balloons or airplanes. Orion and its kin belong to that lineage, visions of dangerous journeys, propelled not by certainty, but by the restless will to go. As you drift with this thought, imagine a starship leaving Earth, not gliding gracefully but thundering into the dark on a chain of nuclear fire, each burst a heartbeat of light against the void. It is both terrifying and beautiful, a reminder that sometimes our imagination runs hotter than our caution, and whether or not such ships are ever built, the dream itself has already served its purpose. It has reminded us that the stars are not unreachable, only costly, and that the cost is written in the language of energy. If distance is the first wall in space travel, then time is the second. Even if you solve propulsion, even if you build ships with enough fuel and power, the journeys stretch across centuries. The gulf between stars is not measured only in kilometers, but in years, decades, and lifetimes. And so the question arises, how do we cross not just the space between worlds, but the time between generations? Einstein's relativity offers a curious gift. It tells us that time is not absolute, but stretches and bends depending on speed and gravity. A traveller who moves close to the speed of light will experience time more slowly than those who remain at rest. This is called time dilation, and it means that a crew could in principle cross light years in what feels like a single lifetime, while centuries pass on Earth. To the travellers, the voyage is survivable. To those left behind, the voyagers return as strangers from the deep future. It is a strange solution, like borrowing from tomorrow to make today longer. But relativity does not come free. To achieve the speeds where time dilation matters significantly requires enormous energy, almost unimaginably more than we can now provide. A ship must be accelerated close to light speed, and the closer it comes, the harder each step becomes. Time dilation dangles before us like a promise, but the price is steep, and it cannot erase the barrier entirely. Even at 90% of light speed, years still pass between stars. The cosmic clock never fully yields. This leaves us with two paths. One is to stretch technology until it bends the rules of distance and duration. The other is to stretch ourselves. Instead of asking whether our ships can survive centuries, we might ask whether our minds can. Here the speculation turns inward. If biology cannot endure the spans required, perhaps consciousness could be transferred, digitized or altered. In theory, a human mind could be encoded into software, carried not as flesh and blood but as streams of data aboard a ship. Electronics can be repaired, replaced, stored in redundant forms. Time that would wither a body might leave information untouched. A digital traveller could cross the centuries without decay, waking on the far side of space much as they were when they departed. Of course, this raises questions as deep as the physics. Would a digital mind still be human? Would it still feel joy, sorrow, wonder? Would it still dream in the same way, or would it think in shapes we could not recognize? The answer is unknowable, but the possibility suggests that perhaps the frontier is not only out there, in distant galaxies, but also within, in what it means to carry a self across time. Biological modification offers another vision. Some creatures on Earth already live for centuries: whales, turtles, certain trees. What if humans could learn from them, altering cells to resist aging, engineering metabolisms to endure long dormancy, or reshaping the body to thrive in artificial habitats? If our lifespans could stretch by orders of magnitude, then journeys of 100 years would no longer seem impossible. Time would still pass, but it would no longer outrun us so easily. Even without such extremes, cultures themselves might adapt. A starship could be launched not as a single crew with a single goal, but as a society with patience embedded in its very design. The mission might be to survive, to continue, to wait. In such a society, meaning would not lie only in arrival, but in continuity, the quiet dignity of carrying forward the hope of one generation to the next, like a candle flame passed along a line of waiting hands. What all these visions share is the recognition that time is not simply an obstacle to be defeated. It is a medium to be endured, shaped, and perhaps even embraced. Relativity may bend it, but cannot erase it. Biology may struggle against it, but cannot escape it entirely. Digital minds may leap past it, but only by changing what it means to live through it. Time is the silent companion of all journeys, and in space it grows louder, reminding us that distance and duration are intertwined. There is a quiet paradox here. We often imagine exploration as movement outward, conquering distance. But in truth, the greater challenge may be learning to live differently with time, to measure our lives not in decades but in centuries, to imagine ourselves not as travellers racing against clocks, but as beings woven into longer rhythms, patient as trees, enduring as stone. Perhaps the ultimate spacefarers will not be those who build the fastest ships, but those who learn to stretch their sense of self across vast spans of waiting. As you let this thought rest, imagine a starship moving silently through the dark, its engines long since shut down, its crew asleep or transformed, its destination still centuries away. To an outside observer, the ship drifts, slow and fragile, but within life persists, whether in flesh or in circuits or in memory itself. The ship is not simply a vehicle, but a vessel of time, carrying human curiosity like a seed across the gulfs of eternity. When you step outside on a clear night and look up, it feels as though the sky stretches forever. The stars seem countless, scattered without end, and it is tempting to imagine that if your eyes were sharp enough, you could simply keep looking farther and farther without limit. But the universe is not endless in what it allows us to see. It carries its own horizon, not made of mountains or seas, but of time itself. The cosmos, as far as we can measure, is about 13.8 billion years old. That number may sound like an abstraction, too large to hold in your mind, but it is not infinite. It is a story with a beginning. Light, though unimaginably fast, still takes time to travel. And so, the farthest we can see is limited by how long the universe has existed. Galaxies whose light has not had time to reach us are invisible, not because they are absent, but because their signals have not yet arrived. They live beyond what is called our observable horizon. Picture yourself standing in the middle of an open field at dawn surrounded by mist. You can see only so far before the fog swallows the view. The world does not end at the edge of that mist, but your sight does. The universe is like that. We are wrapped inside a cosmic fog, bounded not by vapour, but by the finite age of light. Beyond it there may be endless galaxies, stars, even other civilizations, but they are hidden behind the curtain of time, and the horizon is not fixed. It moves as the universe expands. Imagine a ship sailing outward across an ocean while the water itself stretches beneath it. Some shores that were once within reach drift farther away, carried by currents too strong to fight. In cosmology, this is called the expansion of space. Distant galaxies are not flying through the void as if shot from cannons. Instead, the space between us and them is growing. The farther away they are, the faster they recede, and at great enough distances they slip beyond our ability to ever catch their light. This expansion sets a deeper kind of horizon, regions from which light will never reach us, no matter how long we wait. They are receding faster than light, not by breaking the cosmic speed limit, but because the very fabric of space is carrying them away. It is as though we're standing on an island in the middle of a vast sea, and beyond a certain circle the waves carry all things outward, never inward. We can never know what happens there, not because of our tools, but because of the geometry of reality. Even within the horizon, our knowledge carries limits. Astronomers speak of something called cosmic variance. It means that the universe is, in some ways, unknowable, with complete precision simply because we live inside it. We can take only one vantage point from one location, and the universe offers us no second copy for comparison. Imagine trying to measure the average depth of an entire ocean by lowering your bucket into a single spot. Your answer may be close to the truth, but it will never be perfect. The same is true for certain cosmic measurements, like the exact curvature of the universe, or the true distribution of matter at the larger scales. Our answers will always be fuzzy, not because we are careless, but because there is only one cosmos, and we can only look from where we stand. It is tempting to feel discouraged by this, but in another sense, it is a reminder of intimacy. The fact that we cannot see everything does not erase the wonder of what we can see. The galaxies within our horizon already number in the trillions. Each one is a city of stars, each star perhaps a sun with its own retinue of worlds. The cosmos has not starved us of mystery. It has only drawn a curtain at the edges, reminding us that there is always more beyond reach. And horizons themselves are not failures. They are part of the shape of being. When you walk across a plain, you always carry a horizon with you. When you sail across the sea, the horizon never disappears. It only changes its circle. Horizons are not obstacles, but companions, boundaries that define what is close, what is far, and what lies forever beyond. The universe, in its vastness, simply extends this familiar truth into the grandest scale. So when cosmologists say that the universe has a horizon, they do not mean that knowledge is ending. They mean that knowledge has an outline, a frame. Within it, we learn, we measure, we wonder. Beyond it, imagination carries us further than light, and in some quiet way perhaps that is enough. Because even if the cosmos denies us the whole picture, it still offers us a canvas filled with more than any one lifetime could absorb. The fog may surround us, but within it, the lantern of our science glows brightly. As you let this image rest, imagine yourself as a traveller standing at the shore of existence, looking out across a sea that is both visible and hidden. The waves stretch endlessly. The mist curls at the edges, and though you know you cannot see it all, you are still part of what is revealed. The universe gives us horizons not to frustrate us, but to remind us of scale, of humility, and of the quiet beauty of living within a story too vast to ever be told in full. If cosmic horizons remind us that we cannot see everything far away, the quantum world reminds us that we cannot even know everything that is right in front of us. At the smallest scales of reality, knowledge itself becomes blurry, not because of faulty instruments or poor technique, but because nature insists on secrecy. In the 1920s, physicist Werner Heisenberg gave shape to this truth with what is now called the uncertainty principle. It says that there are pairs of things, like the position of a particle and its momentum, that cannot both be known with infinite precision. If you pin one down more clearly, the other slips into vagueness. Try to trap a particle's location, and its motion becomes uncertain. Track its motion closely, and its location spreads like fog. It is not a matter of better tools or sharper eyes. It is not that one day, with a more powerful microscope, we could overcome the fuzziness. The uncertainty is not in our hands, but in the universe itself. Reality, at its foundation, simply does not allow exactness in both at once. Knowledge carries a natural blur. Think of a hummingbird. Its wings a blur of motion as it hovers above a flower. If you stare at the bird's body, you know where it is perched in space, but the tune of its wings becomes a vague whisper in the corner of your eye. If you focus on the wings, listening for the rhythm of their beating, the bird itself seems to dissolve into a flicker. You can hold the place or the song, but never both perfectly at once. This is the way of the quantum, and it goes further. Particles at the smallest scales behave not as neat marbles, but as waves of possibility. They exist not in one definite spot until measured, but as a spread of potential positions like ripples across a pond. The act of observation does not simply reveal what is already there, it helps decide it. It is as though the universe waits until asked a question before settling on an answer. This can sound strange, even unsettling, but it is not chaos. The uncertainty principle does not mean we know nothing. It means we know differently. Instead of predicting the exact path of an electron, we predict probabilities. We say not, here is where it is, but here is where it is most likely to be. Knowledge becomes statistical, a tapestry woven of likelihoods rather than certainties. And in that tapestry lies precision of another kind. Quantum physics, despite its fuzziness, is the most accurate theory we have ever built. It allows us to calculate the magnetic moment of the electron to many decimal places, and the result matches reality with uncanny perfection. It gives us transistors, lasers, magnetic resonance imaging, all tools born from accepting uncertainty as the foundation, not a flaw. So what does this mean for the dream of complete knowledge? It means there are walls not just at the edges of the universe, but at its very heart. Even if you build the finest instruments, even if you gather infinite patience, you will find that some questions cannot be answered in the way you might wish. You can know where, or you can know how fast, but you cannot know both. You can describe possibilities, but not inevitabilities. This uncertainty is not a failure of science, it is its poetry. It tells us that reality is not a hard-edged sculpture, but a living watercolour, its colours bleeding into one another, never confined to sharp outlines. We do not live in a machine where every gear can be mapped and measured. We live in a dance where presence and motion intertwine, and where knowing is always accompanied by mystery. It is easy to imagine that if only we could peer closer, if only we could magnify enough, we might see the bedrock of reality laid bare, solid and final. But the closer we look, the more the ground dissolves beneath us. Electrons are not tiny spheres. Atoms are not miniature solar systems. They are patterns of probability, clouds of perhaps, whispers of almost here and sometimes there. The world is not built of certainty, but of chance shaped into patterns so stable we mistake them for stone. As you think of this, picture again the hummingbird. You can watch its wings or its body, but never both perfectly. Now imagine the universe itself as that hummingbird, always moving, always singing, but never fully caught by our gaze. We listen, we glimpse, we measure, and in the gaps between what we know and what we cannot, wonder takes root. So the uncertainty principle is not only a limit on knowledge, it is also an invitation. It reminds us that reality is not static, but participatory, that to observe is to join the dance, to accept that our knowing is always partial, always shaped by what questions we ask. And in that partiality lies beauty, because it means the universe is not a puzzle already solved, but a song that changes with each listener. If cosmic horizons set limits to what we can see, and quantum uncertainty sets limits to what we can know, then black holes stand where those two limits meet. They are places where distance collapses inward and probability is wrapped tight, leaving us with one of the strangest puzzles in all of physics, the mystery of information. A black hole begins simply. Take enough mass, compress it tightly enough, and gravity overwhelms all other forces. Stars that burn for billions of years eventually exhaust their fuel, and some collapse under their own weight. If the mass is great enough, nothing halts the fall, and the star implodes into a point of infinite density, surrounded by an invisible boundary called the event horizon. The event horizon is not a surface in the usual sense. It has no texture, no solid wall you could touch. Instead, it is a point of no return, the threshold where escape becomes impossible. Anything that crosses it, matter, light, even information, cannot get back out. From the outside, the black hole is silent, offering no clues about what lies within, and this silence deepens. Physicists have shown that from the outside, all black holes look eerily simple. This is sometimes summarized in the phrase, black holes have no hair. No matter what falls in, whether it's a planet, a library of books, or a single photon, the black hole remembers only three things: the total mass, the electric charge, and the spin. Everything else, every detail of history is erased from external view. A star of pure hydrogen and a star of heavy elements, if collapsed to the same mass and spin, become indistinguishable. To the universe beyond, all richness is shaved away. This is troubling, because in physics, information is precious. One of the guiding principles of science is that information cannot simply disappear. Processes may scatter it, hide it, or scramble it beyond recognition, but the sum of information should remain constant. Black holes seem to break this rule, swallowing details and leaving behind only a bland summary. If you drop an encyclopedia into a black hole, the knowledge is gone. If you drop yourself into one, your entire history is reduced to 3 numbers. This conflict is called the black hole information paradox. The paradox became even sharper in the 1970s, when Stephen Hawking showed that black holes are not eternal. Through a subtle quantum process, they emit radiation and slowly evaporate, shrinking over time until they vanish. If this is true, and if the information inside is truly lost, then the laws of physics must allow knowledge to simply vanish from the universe. Many physicists resist this idea because it would unravel the consistency of science itself. And so the paradox remains: does information truly disappear in a black hole, or is it somehow preserved in a way we cannot yet see? One suggestion, strange but elegant, is that the information is not lost, but encoded on the surface. This idea is called the holographic principle. Imagine you walk into a room filled with objects, tables, chairs, books, and discover that everything inside is somehow described by an inscription written on the walls. The three-dimensional story is contained in a two-dimensional script. The holographic principle suggests that a similar thing may be true for black holes. The information about what falls in is not destroyed, but smeared across the event horizon, encoded in microscopic patterns. If this is true, then black holes are not erasers of knowledge but archivists with unusual methods. They keep the record, but only in a form so alien to our senses that it feels like silence. The implication goes even further. The entire universe might work the same way. Some theories suggest that the ultimate amount of information inside any region of space is not proportional to its volume, as you might expect, but to the area of its boundary. This is known as the Bekenstein bound. In other words, the universe may be like a cosmic book where all the words are written on the covers, never in the pages. There is humility in this. We like to think of reality as rich and full of detail, every particle carrying endless nuance. But the mathematics whispers that perhaps the depth we imagine is an illusion. Perhaps information, the ultimate currency of knowing, is not infinite but capped, as if the universe is generous but still keeps a budget. Even if answers come one day, whether the paradox is solved by new physics or by some deep reconciliation between quantum mechanics and gravity, the lesson of black holes will remain. They remind us that there are walls in knowledge not built of distance or of time, but of principle. You cannot peer past the horizon. You cannot recover the hair that is shaved away. You cannot fill a space with more information than its surface can allow. The black hole does not care about our desire to know. It enforces its boundaries with the weight of space-time itself. And yet, there is also beauty here. Black holes, those silent guardians of secrecy, are among the most luminous teachers of physics. By wrestling with their paradoxes, scientists have uncovered new ideas about entropy, quantum fields, and the holographic nature of the universe. Their silence speaks, not in words, but in constraints that force us to imagine reality differently. As you let this settle, picture a black hole not as a monster devouring light, but as a horizon etched with hidden script. You cannot read it directly, but you can sense that it is there, a boundary where knowledge changes form. It is the quiet wall where the universe whispers, some things will always be hidden, but in the hiding lies a deeper story. When you look at a lake from far away, its surface seems smooth like glass. But as you walk closer, you notice ripples. Closer still, and you see tiny waves stirred by insects and wind. If you could shrink yourself down further, you would find that even the smoothest water is restless, molecules colliding, vibrating, forever in motion. At each scale, what seemed calm reveals new turbulence. Physics suggests that space-time itself is like that. From a distance, it looks smooth and continuous, a silent stage on which galaxies drift. But deep down, at the smallest conceivable scale, it may boil with ceaseless energy. This restless foundation is called quantum foam. The limit is set by something called the Planck scale. Named after Max Planck, one of the founders of quantum theory, it defines the smallest meaningful length and the shortest meaningful time. The Planck length is unimaginably tiny, about 10 to the negative 35th meters, so small that if an atom were the size of the entire observable universe, the Planck length would be the size of a tree. The Planck time is the time it takes light to cross this distance, about 10 to the negative 43rd seconds. Below these scales, our current understanding of physics, both quantum mechanics and general relativity, simply breaks down. Why? Because our two great theories, brilliant in their own domains, clash here. Quantum mechanics governs the very small, where uncertainty and probability rule. General relativity governs the very large, where space-time bends and curves under the weight of matter. At ordinary scales, the two coexist peacefully. But at the Planck scale, both must be considered at once, and when we try, their equations explode into contradictions. It is as though the universe has drawn a line and said, "You may look this far, but no further, not yet." Physicists imagine that at these scales, space-time is not smooth, but frothy. Tiny fluctuations cause it to bubble and writhe like boiling water, creating a foam of ever-changing geometry. Wormholes blink in and out, connections form and dissolve, distances lose meaning. The fabric of existence itself becomes a storm of possibility. We cannot see it directly, but the mathematics suggests that beneath the calm surface of reality, this froth may churn eternally. And here lies another ultimate limit. Even with perfect instruments, even with infinite patience, it may be impossible to resolve anything below the Planck length. Like trying to peer into water with a magnifying glass until the very notion of surface disappears, we find that the act of measurement itself disturbs what is measured. Any attempt to probe smaller scales requires more energy, but beyond a point that energy collapses into a black hole, hiding the very detail we sought. Reality guards its foundation with paradox. Gentle comparisons can help. Imagine you are trying to examine the weave of a fabric by shining brighter and brighter light upon it. At first, the added brightness reveals more threads, but keep increasing the intensity, and instead of clarity, you burn a hole through the cloth. The detail you wanted is gone. The Planck scale is that threshold for the universe. To press harder is not to see more, but to undo the very thing you wish to see. This flaw is humbling. We are accustomed to thinking that with finer instruments we can always peel back another layer. Better microscopes, better telescopes, better sensors. Progress has always meant zooming deeper or farther. But at the Planck scale, there may be no more peeling to do. Reality does not stretch down into an infinite stack of smaller and smaller bricks. Instead, it may blur into foam, a shimmer of geometry where space and time are not continuous, but emergent. And yet, as with all limits, the floor of reality is not only a wall, but a guide. By chasing it, scientists are building new theories that might one day unite quantum mechanics and gravity. Ideas like string theory and loop quantum gravity attempt to describe what space-time looks like at this restless depth. They may succeed or they may fail, but in their striving they show us something profound. That even the floor itself may not be fundamental, but the doorway to a deeper description. For now, though, the foam remains hidden, sensed only through faint whispers in equations, and perhaps that is fitting. Just as the surface of the sea looks calm from the shore, the universe spares us its turbulence until we are ready to approach. We live in the middle scales, where atoms form, where stars shine, where galaxies drift gracefully. The violence beneath is there, but softened, blurred, distant. It is a reminder that our experience is not the whole of reality, but a carefully chosen layer, one where life can breathe. So when you hear that there is a smallest length, a shortest time, do not think of it as a barrier closing doors. Think of it instead as a pause in the infinite descent, a place where the universe says softly, "Enough." It is not a cruelty, but a kindness. Because without such a flaw, perhaps reality would dissolve into endless regress, and nothing stable could ever emerge. The foam may be restless, but it is also fertile. Out of its storm, the smooth fabric we call space is woven, and upon that fabric stars burn and minds wander. As you drift into rest, imagine standing at the edge of a vast ocean at night. The surface looks calm, moonlight glimmering across the waves. But you know, deep beneath, currents churn, creatures move, pressures rise. You do not need to see every detail to feel the presence of something greater than yourself. The Planck scale is like that ocean's depth, hidden, restless, unreachable. And yet, It holds you, carries you, sustains the world you live in. If there is one idea that can unsettle both scientists and poets alike, it is the idea of infinity. At first it seems simple, just keep counting. 1, 2, 3, 4, and so on. Numbers stretch ahead like a road without end. You can always add one more, no matter how far you've gone. Infinity begins as a whisper at the edge of arithmetic, a promise that there is always another step. But when you look closer, infinity does not behave like a larger number. It behaves like something entirely different, something that breaks the habits of our thinking. Consider a simple thought experiment. Imagine a hotel with an infinite number of rooms. This story was first told by the mathematician David Hilbert, and it is often called Hilbert's Hotel. The hotel has rooms numbered 1, 2, 3, and so on, all the way to infinity. Now imagine that every single room is full. In an ordinary hotel, that would mean no new guests could be admitted. Full is full. But in Hilbert's Hotel, there is always room for one more. The manager simply asks every guest to move to the next room. Those in room 1 move to room 2. Those in room 2 move to room 3, and so on forever. Suddenly, room 1 is empty, and the new guest can check in. Despite being full, the hotel is never truly full. Already the intuition trembles. Infinity is not like a very large number. It is slippery. Add 1, and it does not grow. Subtract 1, and it does not shrink. You can even add infinitely many new guests, say, an infinite busload arrives, and still find places for them by shifting everyone into even-numbered rooms. The odd rooms become vacant, and the infinite newcomers settle in. Infinity absorbs everything without strain. In daily life, this feels absurd. Imagine standing in a bakery asking for an infinite loaf of bread. If the baker cuts off a slice for you, does the loaf shrink? In the world of numbers, the answer is no. Infinity remains untouched. A slice, or even infinitely many slices, does not reduce it. What makes sense in a bakery collapses in Hilbert's Hotel. This is why infinity is not counted among ordinary numbers. It does not sit at the end of a line waiting to be reached. It is a horizon, always beyond, always elusive. You can run toward it, you can double your pace, you can imagine machines counting faster than the human mind can follow, and still you will never arrive. Infinity is the race that never ends, the staircase with no last step, the ocean without a shore, and it comes in different sizes. This is another twist, first revealed by the mathematician Georg Cantor. The infinity of counting numbers, 1, 2, 3, and so on, is vast, but the infinity of points on a line, like those between 0 and 1, is larger still. There are infinities within infinities, nested like Russian dolls, some countable, some uncountable. You might think infinity is the final ultimate vastness, but even there, hierarchies emerge. The infinite is not uniform but layered, complex, unfolding, in ways no finite mind can fully hold. What does this mean for us here, listening in the quiet? It means that infinity is not a comfortable companion. It is a concept that stretches logic until it creaks. It allows hotels that are always full but never full, bakeries that never run out of bread, staircases that never end but also never begin. It makes us realize that numbers, which feel so solid in the small, become strange when they grow without bound. And yet, this strangeness is not useless. Infinity is a real tool in mathematics, used to describe limits, to calculate areas, to understand processes that continue without end. Without it, calculus would crumble, and modern physics would lose one of its sharpest blades. Infinity is not fantasy. It is a framework, but it is also a reminder that human intuition, born in a finite world of loaves and rooms, does not extend cleanly into endlessness. Perhaps this is why infinity feels both beautiful and haunting. To contemplate it is to stand on the edge of comprehension. You cannot see it whole, but you can feel its pull. Like standing by the ocean at night, hearing waves that never stop, you know there is more water than you could ever measure. Infinity does not ask to be solved. It asks to be acknowledged, and in this acknowledgement lies humility. When we imagine knowing everything, when we dream of a final equation or a complete map of reality, infinity steps in to whisper otherwise. Knowledge cannot be complete if the subject is unending. Counting cannot be finished if numbers refuse to stop. The universe, if infinite, is not a puzzle to be solved, but a landscape to be wandered, without end. So infinity, far from granting ultimate knowledge, may guarantee its impossibility. If there is no end, then there is no final page to turn, no last digit to write, no ultimate cosmic ledger with everything tallied. Infinity means the story continues beyond every ending we can imagine. As you let this settle, think again of Hilbert's Hotel, a hallway that never finishes, doors opening forever, each with someone inside and always space for one more. It is a strange comfort, endlessness woven into the fabric of logic itself. You cannot check out of such a hotel, for its corridors extend without end. You can only walk, knowing that the journey will never be finished, and maybe that is what infinity is, the gentle reminder that some journeys are not meant to conclude. Infinity in mathematics already bends our thinking, but when physics borrows the idea, it becomes even stranger. What if infinity is not just about numbers or abstract hotels, but about reality itself? What if our universe, the galaxies, the stars, the atoms, the lives we know, is only one room in a much larger hotel of existence? This possibility is called the multiverse, and it has become one of the boldest and most bewildering frontiers of modern thought. To make sense of it, physicist Max Tegmark offered a ladder of possibilities, described as levels 1 through 4. Each level imagines a different way that reality might extend beyond what we see. Level 1 is perhaps the simplest. It sees that space itself might be infinite. If the cosmos goes on without end, then beyond our horizon, beyond the curtain of light we cannot yet see, there are other galaxies, other stars, perhaps even other planets that look remarkably like ours. Given enough space, every possible arrangement of matter must eventually repeat. Somewhere, unimaginably far away, there could be another Earth, another version of you sitting under another night sky, wondering the same things. Not because of magic, but because infinity demands repetition. Level 2 steps further. It emerges from the theory of eternal inflation, which suggests that the Big Bang was not a single explosion, but part of an endless process. Space inflates, like dough rising, but instead of filling evenly, it forms bubbles, regions where inflation slows and matter condenses into stars and galaxies. Each bubble becomes a universe, with its own laws, its own constants of nature, perhaps even different dimensions. Our universe is just one bubble, and there may be countless others, forever budding, forever drifting away. Imagine an endless pot of boiling soup, each bubble a cosmos with its own recipe. Level 3 turns inward, to quantum physics. According to the many worlds interpretation, every quantum choice branches into multiple outcomes. When a particle has two possible paths, the universe does not choose one and discard the other. It realizes both in separate branches of reality. In one, the electron goes left. In another, it goes right. In one, you choose tea. In another, you choose coffee. The multiverse here is not far away but layered alongside us, shadow realities that unfold with every quantum event. Level 4 is the most radical. It suggests that all mathematical structures exist as realities. Every consistent set of equations describes not just an abstract possibility, but a genuine universe. Our cosmos, with its particles and forces, is just one instantiation of mathematics. In this vision, reality itself is math, and the multiverse is the library of all possible equations, all possible worlds. These levels differ in flavour, but they share a theme: the idea that our universe is not all there is. Instead of one book of existence, there may be a library without walls. Instead of one sky, there may be skies upon skies, stacked, branching, multiplying without end. But this multiplication comes with challenges. The further we climb, the harder it is to test. Level 1, infinite space, is plausible though unprovable. Level 2, eternal inflation, has some footing in cosmological models, though evidence remains indirect. Level 3, many worlds, makes predictions that are difficult to distinguish from ordinary quantum mechanics. And Level 4 moves so far beyond physics into philosophy that it blurs the line between science and speculation. Still, the pull of the multiverse is strong. It offers explanations for puzzles. Why are the laws of nature tuned just so, allowing stars to burn and life to emerge? In a multiverse of many laws, most universes would be barren, but in some, like ours, the conditions would permit life, and it is no surprise that beings arise there to ask the question. The multiverse explains our luck not as design, but as a lottery with infinite tickets. And yet, with its allure comes unease. If every possibility is realised somewhere, what does it mean to say something is true? If there are versions of you who made every possible choice, then who are you really? Are you the sum of all versions, or just one branch that happens to carry your awareness tonight? Infinity, when married to the multiverse, does not just stretch space, it stretches meaning. For many scientists, the multiverse remains controversial, not because it is impossible, but because it may lie beyond observation. If we can never cross into another bubble, if we can never peek at another branch, then is it science or poetry? Perhaps both. Science often begins as poetry, an imaginative leap that later finds grounding. The multiverse for now may be such a leap. As you let these ideas rest, picture yourself walking through a library at night. The shelves stretch endlessly in every direction. On each one, books contain every story that could ever be told. Some are familiar, others strange, others unreadable. You pick one volume, and it happens to be this life, this earth, this cosmos. But the shelves do not end. The library is the multiverse, and whether we can ever leave our aisle or not, it reminds us that the story we know is not the only one that could exist. If infinity already unsettles mathematics, and if the multiverse suggests that infinity might be stitched into the fabric of reality itself, then another question quietly arises. How do you measure anything in a world where everything happens infinitely many times? This is called the measure problem, and it strikes at the heart of what it means to know something at all. Imagine rolling a die. In a finite world, the math is straightforward. 6 sides, 6 possibilities, each with a probability of 1 in 6. Roll enough times and the numbers balance out. But now imagine rolling not 6 times, not 1,000, not even 1,000,000,000, but infinitely. In an infinite series of rolls, every number comes up infinitely many times. 1 appears infinitely, 2 appears infinitely, and so on. Suddenly the fractions that once guided us collapse. Infinity divided by infinity leaves no clear answer. The die becomes not a tool of probability, but a symbol of its breakdown. This is more than a mathematical curiosity. If the multiverse is infinite, then every possible outcome is realized somewhere. Somewhere, there is a universe where a coin lands heads forever. Somewhere, another where it lands tails forever. Somewhere, you made every possible choice, turned left instead of right, stayed instead of leaving, spoke instead of staying quiet. Each of these possibilities unfolds not once, but endlessly. In such a landscape, how do we say what is likely or even what is meaningful? Physicists run into this problem when they try to calculate predictions in cosmology. If eternal inflation creates infinitely many bubble universes, then how do you count them? If each bubble contains infinitely many galaxies, how do you compare one to another? Probabilities, which work so well in the finite, start to unravel in the infinite. You cannot simply tally and divide because both the numerator and denominator are endless. Depending on how you try to cut infinity into slices, you can get wildly different answers. The measure problem is not that we lack data. It is that in an infinite cosmos, data itself has no stable foundation. Here a gentle metaphor helps. Imagine you are standing in an orchard that stretches forever. Trees line up in all directions without end. Some trees grow red apples, some grow green, some both. If you try to ask, what fraction of apples in the orchard are red? The answer depends entirely on how you count. Start with one row and you may find mostly red. Start with another and you may find mostly green. Try to count them all and the question dissolves because there is no all to be reached. The orchard is infinite. Every proportion is slippery, every fraction suspect. And yet, we crave certainty. We want to know, if the cosmos is infinite, what we should expect. If we meet other civilizations, how common should life be? If there are infinite Earths, how often do they host beings like us? But in infinity, frequency becomes a fog. There are not 10 red apples for every green, or even 1,000,000 for every billion. There are infinitely many of each. What matters locally may vanish globally. This creates a strange paradox. Knowledge, which feels like the art of generalizing, becomes fragile in the infinite. Science works by finding patterns and projecting them outward, by saying, because we saw this here, it will be true there. But in an infinite multiverse, there is no guarantee that the local pattern is universal. Every rule has exceptions somewhere, and every exception repeats endlessly. Probability, the bridge between the known and the unknown, loses its footing. Some thinkers suggest that perhaps the infinite cannot be fully grasped with the tools we have. Just as uncertainty limits our knowledge of the very small, infinity limits our knowledge of the very large. We may need new mathematics or new principles of selection to make sense of it. Others suggest that perhaps we should not ask global questions at all. Instead of wondering, what is true across all universes? We might accept that only local truth matters. What is true here, in this branch, in this horizon? There is humility in that shift. It means that knowledge is not the final map of everything, but the story of where we stand. It is like living in an endless forest and realizing you cannot catalogue every tree. Instead, you learn the grove around you, the paths you walk, the seasons you feel. The infinite forest stretches on, unknowable, but that does not erase the meaning of what you see here. Knowledge becomes intimate, not universal. And perhaps that intimacy is enough. Infinity may dissolve probabilities, but it also guarantees abundance. Every possibility exists not once, but endlessly. Every dream, every experiment, every story is played out somewhere. You may not know the measure, but you can know that nothing is truly excluded. That is both dizzying and comforting. Infinity is not cruel. It simply refuses to be counted. As you drift into rest, imagine holding a pair of dice in your hand. You roll them once, and the numbers land. In some universe, they land differently. In another, they never stop rolling. In another, the dice do not exist at all. The measure problem whispers that in infinity, all outcomes are realized. But it also whispers that what you hold, here and now, is still real, still precious, still the outcome that belongs to you in this branch of the cosmos. There is something comforting about mathematics. 2 + 2 will always be 4. Triangles will always have 3 sides. Numbers and their patterns feel timeless, unshakable, immune to the drift of opinion. While the universe may shift, While stars burn out and galaxies dissolve, a theorem written on paper seems to outlast them all. It is no wonder that philosophers once dreamed mathematics might be the key to complete certainty, that every truth, no matter how complex, could someday be derived by reason alone. If we only had enough patience, enough time, enough cleverness, the thought was that all knowledge might be proven. But in the early 20th century, a quiet, brilliant logician named Kurt Gödel disrupted that dream. His work is known as the incompleteness theorems, and their message is as haunting as it is profound. No matter how powerful your system of logic, there will always be truths that cannot be proven within it. Mathematics itself is incomplete. The idea can sound abstract, but let us bring it closer. Imagine you are working on a vast jigsaw puzzle, one so large that it stretches across an entire table. You have placed thousands of pieces and the picture has begun to emerge. Mountains, rivers, skies. With each piece, the satisfaction grows. But then you realize something strange. No matter how many pieces you place, there are always gaps that cannot be filled, spaces that seem to demand shapes that do not exist in the box. No matter how much you search, the puzzle will never be complete. Gödel's theorems whisper that mathematics is like that puzzle. You can build as much as you want, but there will always be missing pieces, true statements that exist, but which the system cannot prove. Another analogy: imagine a library with infinitely many books. Each one contains a proof, a theorem, a deduction. You can read for a lifetime, and every book is precise and meaningful. But hidden among the shelves are truths that cannot be written down, not because they are false, but because the language of the library cannot contain them. They are like melodies that exist, but cannot be transcribed in the available notes. The library is rich, but never complete. Gödel's insight emerged in response to a dream known as Hilbert's program. The mathematician David Hilbert believed it might be possible to formalize all of mathematics, to reduce it to a perfect logical machine. Every theorem would follow from a finite set of axioms, basic truths accepted without proof, and all questions could eventually be answered. It was a vision of total knowledge, as if mathematics were a cathedral whose walls could rise endlessly without crack or shadow. Gödel gently, almost reluctantly, showed that the vision was impossible. For any consistent system powerful enough to include arithmetic, there will always be propositions that are true but unprovable within that system. To prove them, you must step outside, expand the system, add new axioms. But then, within that new system, other truths slip away, still beyond reach. The horizon always recedes. The consequences ripple far beyond logic. If even mathematics, the realm of abstract certainty, is incomplete, then the dream of perfect, all-encompassing knowledge falters. It does not matter how powerful your reasoning, how tireless your machines. There will always be questions that resist. Truth is larger than proof, and yet there is beauty in this limit. Gödel did not destroy mathematics. He deepened it. He showed that truth is not confined to what can be written in symbols, that mystery is not a flaw, but a feature of thought itself. Just as the night sky seems more beautiful for its unreachable stars, mathematics is richer for its unreachable truths. Consider again the puzzle analogy. If every piece fit perfectly, if nothing were missing, the satisfaction might be neat but dull. It is the gaps, the spaces that hint at something beyond, that give the puzzle its endless intrigue. Gödel gave us those gaps, not as despair, but as wonder. For science, the incompleteness theorems are a quiet reminder that we should be humble. We may build models of the universe, equations that predict and explain, theories that reach astonishing precision. But the very structure of logic itself guarantees that some truths will remain out of reach. Knowledge is not a ladder that ends in heaven, but a bridge that stretches only so far with mist beyond. For philosophy, the theorems reopen ancient questions. If truths exist that cannot be proven, then truth itself is larger than formal reasoning. Perhaps intuition, creativity, or even other modes of knowing play a role in glimpsing what proof cannot capture. The border between the known and the unknowable is not a wall but a porous frontier, a landscape of shadow and suggestion. As you let this rest, imagine walking through that infinite library again. Row upon row of shelves stretch into the dark, filled with books of impeccable logic. You take one down, read its precise lines, and marvel at the clarity. But you know, somewhere in that library truths are missing. Not errors, not mistakes, but melodies too vast for the available notes. You close the book and smile, because incompleteness is not failure. It is the guarantee that thought will never run dry, that there will always be more mystery to chase. Gödel's work reminds us that knowing is not about reaching a final end, but about walking a path that never exhausts itself. The puzzle will always have open spaces, the library will always have unwritten melodies, the cosmos will always have horizons. That is not a reason to despair. It is a reason to keep wandering, to keep reading, to keep fitting pieces as far as we can, and perhaps that is the most peaceful realization of all. We do not need to know everything. We cannot. But in that impossibility lies the endless unfolding of wonder, a promise that mystery itself will never vanish. Like a lullaby that never finishes, it will always carry us gently onward into the quiet. When you open your eyes, you change the world around you. That sounds poetic, but in quantum physics it is also quite literal. The act of observing is not passive. It does not simply reveal what is already there. Instead, it reshapes reality in subtle ways, leaving us to wonder whether we can ever know the universe as it is, independent of our looking. This is sometimes called the measurement problem. At its heart lies a puzzle. In quantum theory, particles such as electrons or photons do not exist in neat, well-defined states until they are observed. Instead, they are described by wave functions, mathematical clouds of probability. An electron is not here or there, but smeared across possibilities. It has many futures, many options, many overlapping selves, but the moment you measure it, say, by shining light to detect where it is, the cloud collapses. One possibility becomes actual, and all others fade away. The difficulty is that we do not really know why or how this collapse occurs. Does observation force the choice? Does the measuring device? Does the universe itself split into branches where every option is realized? The theories differ, but they agree on one unsettling fact. To know the quantum world is to disturb it. An everyday metaphor might help. Picture an oven where bread is slowly rising. The heat and steam are doing their delicate work, shaping the crust, softening the crumb. But if you open the oven door, even for a moment you change the process. The rush of cooler air interrupts the balance. The bread you pull out is not the bread that would have emerged had you never peeked. The act of checking alters the outcome, so it is with particles. To observe them is to jostle them, to open the oven of the quantum world and let in a draft. Or think of trying to weigh yourself on a trampoline. You step on, and the surface bends under your weight. The scale cannot give you a number without changing the very thing it measures. In the quantum world, every measurement is like that trampoline. Observer and observed are tangled together. This strangeness has been tested again and again. The double-slit experiment is a classic example. Fire particles at two narrow openings, and they form a pattern of interference, as if each particle is a wave exploring both paths at once. But when you try to watch which slit a particle passes through, the pattern vanishes. The very act of measurement collapses the wave into a particle, erasing the interference. The world you see depends on whether you look. It is tempting to think of this as a flaw in our instruments, a technical problem. But even the most delicate tools designed to minimize disturbance cannot escape it. The principle is woven into the fabric of reality. To measure is to interact, and to interact is to alter. There is no clean separation between the knower and the known. This has profound consequences for the dream of perfect knowledge. If every act of observation changes what is observed, then the universe cannot be known as a pristine, untouched object. We are always part of the experiment, always a participant, never a detached spectator. Knowledge is not a window that lets us peer in from the outside. It is a mirror, reflecting us as we try to see the world. Some interpretations of quantum mechanics, like the many worlds view, soften the paradox by suggesting that all outcomes happen, each in its own branch. When you look at the particle, you do not collapse its possibilities. You simply follow one thread of reality, while others continue without you. In this picture, the act of observation does not destroy possibilities but divides them. Yet even here, certainty remains elusive. You never see the other branches. You never know the fullness of the wave. Other interpretations, like objective collapse theories, propose that wave functions decay spontaneously, with or without observers. The universe itself chooses, in hidden ways we cannot yet grasp. Still others suggest that reality is fundamentally relational, that what exists is not independent objects, but the relationships created in acts of interaction. Whichever interpretation you favour, the message is similar. There are boundaries to what can be known. Not boundaries of distance, like the edge of the observable universe, but boundaries built into the act of knowing itself. And this carries a humbling lesson. We often imagine knowledge as peeling back layers of reality until we reach the core, the final truth beneath all appearances. But in quantum mechanics, there may be no core untouched by the act of peeling. Every layer reshapes itself in the moment we look. The truth is not static, waiting to be revealed, but dynamic, intertwined with our presence. This does not make knowledge meaningless. On the contrary, it makes it more precious. Each experiment, each observation is not a simple unveiling, but a collaboration between us and the universe. We shape the outcome as much as we discover it. Science becomes not a conquest, but a conversation, an ongoing dialogue in which reality responds to our questions, not always with clarity, but always with resonance. As you reflect on this, imagine yourself standing before a still pond at dawn. You long to know what lies beneath the surface. You reach out with a pebble, drop it into the water, and ripples spread. The pond answers, but in answering it changes. You cannot separate the truth from the ripples. You cannot know the pond as it was without you. And yet, in those ripples lies information, beauty, and connection. The pond does not give you everything, but it gives you something. And that something is enough to keep you coming back, watching, wondering. So it is with the universe. The problem of measurement is not a flaw, but a reminder. Knowledge is always shared, always shaped, always unfinished. We do not simply observe the cosmos. We touch it, and in touching, we become part of the story it tells. For all the vastness of the cosmos, the real boundary of knowledge may lie much closer, inside our own heads. Human brains are remarkable. They have carried us from stone tools to spacecraft, from counting sticks to quantum mechanics. Yet they are also products of evolution, sculpted not for completeness, but for survival. Our ancestors did not need to calculate particle fields or navigate galaxies. They needed to find food, avoid predators, and cooperate with one another. The brain is a marvel, but it is also a compromise, built with shortcuts and blind spots. Consider how easily we are fooled by illusions. A set of lines can appear longer or shorter, depending on the arrows drawn at their ends. A shadow can make one square look darker than another, even when both are the same shade. Our senses, though reliable enough to keep us alive, are not perfect instruments of truth. They are tuned for usefulness, not for ultimate accuracy. And even when abstract reasoning takes over, We carry those limitations with us. We are prone to bias, to error, to overconfidence. We see patterns where none exist. This suggests that there may be truths we cannot even frame as questions, let alone answer. Just as a dog may never grasp algebra, or a fish may never imagine fire, there may be aspects of reality forever beyond the reach of human minds. The cosmos could be full of dimensions of truth that we simply cannot perceive, like colours outside the range of our vision. It is here that some look to machines. Artificial intelligence promises not just faster calculation, but different ways of thinking. Already, AI can sift data at scales no human can match, find patterns invisible to us, and generate insights we might overlook. It is tempting to imagine that AI could become the ladder beyond our ceiling, extending knowledge into realms where human intuition fails. Perhaps an artificial mind could frame questions we cannot even articulate and perceive truths that lie outside our cognitive horizon. But here again, limits return. For AI, like us, is bound by the mathematics it runs on and the physical universe it inhabits. An algorithm may rearrange data in alien ways, but it cannot escape Gödel's incompleteness. A neural network may simulate creativity, but it cannot bypass the quantum uncertainty that shapes all measurement. The machine inherits our boundaries, even as it extends our reach. There is also the question of whether intelligence itself is infinite or bounded. If every mind, biological or artificial, must operate within some system of logic, then every mind will encounter truth that cannot be proven, questions that cannot be answered, walls that cannot be crossed. It may not matter how powerful the processor is, or how vast the dataset becomes. At some level, knowledge ends not in omniscience but in silence. A gentle metaphor can help here. Imagine a hall of mirrors. You hold up a candle, and its image reflects endlessly in the glass. You see copy after copy stretching into the distance. But no matter how many reflections appear, they never show what lies outside the hall. Mirrors can multiply what is inside, but they cannot reveal the world beyond. Minds, human or artificial, may be like those mirrors. They can reflect, extend, recombine, but they cannot capture what lies fundamentally outside their frame. And yet, this does not make them meaningless. The reflections in the Hall of Mirrors may not reveal the outside world, but they are still beautiful, still full of light. The knowledge we gain may never be complete, but it is still wondrous, still transformative. Each discovery, each insight, is a reflection that adds to the pattern, even if the whole cannot be seen. It is also possible that minds do not need completeness to find meaning. The limits themselves may be what keep curiosity alive. If we could know everything, perhaps there would be no drive to explore, no spark of wonder. It is the gaps in our vision, the mysteries we cannot quite resolve, that keep the story moving forward. Our ceilings may not be failures, but gifts, reminders that the universe always has more to offer than we can grasp. AI, then, is not our replacement, but our companion in this shared ignorance. Together, humans and machines may map more of the mystery than either could alone, but they will never drain it dry. Every answer will open new questions, and every horizon will lead to another horizon. The mirrors will keep reflecting, but the silence beyond them will remain. As you settle into the thought, imagine standing before a dark lake at night. The water is still, and the stars shimmer in reflection. You see thousands of points of light rippling on the surface. You know they are not the stars themselves, only their echoes. But the sight is no less beautiful for that. Knowledge too is like those reflections. It may never capture the stars in their entirety, but it gives us their shimmer, their presence, their guidance. And that is enough to keep us walking, thinking, and wondering. In the end, the limits of minds, our minds and the minds we build, are not the end of the story. They are the quiet assurance that mystery will always remain, that wonder will never be exhausted, that truth is larger than proof, larger than observation, larger than any mirror can contain. And in that assurance, perhaps, lies the most peaceful knowledge of all. When you look back across history, it is hard not to notice a pattern. Humanity has a habit of declaring something impossible, only to find, centuries later, that the boundary has shifted or dissolved entirely. What once seemed like a wall turns out to have been a doorway, just waiting for the right key. This does not mean that all limits can be moved, but it does remind us to be humble about declaring what cannot be done. Think of flight. For most of human history, the dream of flying was left to birds, to myths, and to the imagination. People gazed at the sky, carved wings, built contraptions of wood and feathers, and almost always failed. For millennia, the very idea of human flight was treated as a fantasy. And then, one morning in 1903 at Kitty Hawk, the Wright brothers lifted off the ground for 12 seconds. It was not long, and it was not high, but it was enough to cross the line between dream and reality. Today, air travel is so ordinary that people complain about legroom and reheated meals while cruising 6 miles above the Earth at hundreds of miles per hour. The hard wall, it turned out, was a door. The same is true in medicine. For thousands of years, diseases were seen as punishments from gods or mysteries without remedy. The plague swept through medieval cities without resistance, leaving millions dead. But slowly, through microscopes and careful observation, hidden worlds of bacteria and viruses were revealed. Vaccines were developed, antibiotics discovered, surgeries refined. What once seemed inevitable, disease as an unavoidable limit of life, has become a realm where knowledge bends the arc of fate. The average human lifespan has more than doubled in just the past 2 centuries. Again, the wall was not permanent. Even our perception of distance has changed. For most of history, crossing the ocean was a journey of months, fraught with storms and hunger. To send a message across continents required riders, ships, or couriers carrying scraps of paper. Then came the telegraph, the telephone, and the satellites that now ring the Earth. Today, a message can circle the globe in less than a second. Space and time have not changed, but our reach across them has. A frontier that once seemed fixed has softened. These examples remind us that many of the limits we face are not laws of physics, but challenges of imagination, engineering, or patience. What one generation declares to be impossible, the next may treat as routine. Consider biological limits. For most of history, human life was thought to end naturally around 40 or 50 years. Old age was a rare privilege, often accompanied by frailty and decline. But now, advances in medicine, nutrition and genetics are stretching that horizon. Some researchers even imagine futures where aging itself could be slowed, or where damaged organs might be repaired by stem cells and nanotechnology. The limit of lifespan may not vanish, but it may move. Cognition too has been stretched. Once, a single human mind could hold most of the world's known knowledge. Today, the sum of human understanding is so vast that no one person can contain it. But we have created tools, books, computers, networks that extend memory and thinking beyond any one brain. Artificial intelligence is only the latest expression of that extension. While it will not erase the ultimate boundaries of thought, it may widen the circle of what is reachable. In this sense, the mind itself is not limited to the skull. It stretches into the tools we build and the communities we form. Energy, once considered scarce, is also expanding in possibility. For centuries, wood and muscle were the primary fuels of civilization. Coal and oil transformed that, giving us industry, flight, and electricity. Now, we are learning to capture sunlight, to harness wind, to split atoms. Tomorrow, perhaps, we will control fusion, the process that powers the stars. Each new step reveals more of the universe's potential to be tapped, and with it, more doors of discovery may open. This is not to say that every limit can be overcome. Many are real, as we will soon explore, but it's worth remembering that walls sometimes only look solid from a distance. When approached carefully, with patience and curiosity, they reveal seams, cracks, hidden hinges. A gentle metaphor: imagine walking through a forest and coming upon a dense thicket of brambles. At first glance, it seems impenetrable. The branches are twisted, the thorns sharp, the shadows thick. But if you pause, if you step closer, you may notice a narrow gap, a deer path hidden in the undergrowth, a passage you had not seen before. What looked like a wall becomes a doorway, leading you deeper into the forest. Knowledge has often unfolded in just that way. In the story of science, every great leap has carried this lesson. Telescopes opened the heavens, microscopes unveiled the tiny worlds, computers revealed patterns in chaos. Again and again, the boundary shifted. Each time we reached the edge of knowing, we discovered it was not the end, but the beginning of a new trail. As you reflect on this, you may notice a soft reassurance. If limits can shift, then the future is not fixed. Our capacity to learn, to imagine, to explore may stretch in ways we cannot yet picture. Some ceilings may rise higher, some walls may swing open. The chest of knowledge may never be fully unlocked, but its lid is not nailed shut. With effort and time, it can be pried open a little wider, and perhaps that is enough. We do not need to know everything to find wonder. It is enough to know that the path does not end where we stand, that there are doors waiting in the thickets, horizons that move when we reach for them. Humanity has always walked that path, and will continue to do so, step by step, discovery by discovery. The walls are many, but so are the keys. For every wall that turns out to be a door, there are others that remain locked no matter how we tug at them. The story of human knowledge is not only one of expanding horizons, but also of running up against boundaries that seem to be written into the fabric of the universe itself. These are not the kind of limits that crumble with new tools or clever ideas. They are the kind that endure, unyielding, no matter how advanced we become. One such wall is the Planck scale, the realm where our usual descriptions of reality dissolve. At distances of about 10 to the negative 35th meters, and times of about 10 to the negative 43rd seconds, space and time no longer behave as smooth, continuous fabrics. Instead, they are thought to froth like a restless sea, bubbling with quantum foam. Our equations cannot resolve detail beyond this scale. They blur, like a painting viewed too closely until all that remains are smudges of colour. No telescope, no microscope, no collider can reveal structures smaller than this. It is not merely a technological shortcoming, but a fundamental resolution limit, as if the universe itself has chosen a smallest pixel, a final grain beyond which no image can sharpen. Another immovable limit is the cosmic horizon. The universe is about 13.8 billion years old, and light has had only that much time to travel. Beyond a certain distance, farther galaxies recede faster than their light can reach us, pulled away by the expansion of space itself. No matter how long we wait, no matter how clever our instruments, those regions remain forever hidden. They are not merely out of sight, they are unreachable. The cosmos contains oceans of mystery that will never lap at our shores. We live inside a bubble of the observable, and the walls of that bubble harden with time. Then there are the information bounds. Black holes are the starkest illustration. According to the no-hair theorem, a black hole, no matter what fell into it, reveals to the outside world only three numbers: mass, spin, and charge. The details of what collapsed, stars, planets, even entire civilizations, are erased from external view. The event horizon acts as a one-way veil. For decades, physicists argued over whether the information was truly lost or encoded somehow at the boundary, a debate wrapped up in the so-called black hole information paradox. Whichever resolution proves correct, one truth remains: information is not infinitely retrievable. The universe imposes ceilings on how much can be stored, processed, or known, limits expressed in ideas like the Bekenstein bound and the holographic principle. Reality itself has a maximum capacity for information, like a chest that can only hold so many joules, no matter how small you try to cut them. And then there is infinity. At first it seems generous, endless possibilities, limitless numbers, eternal space. But infinity is less a gift than a complication. In mathematics, infinity breaks our intuition. Hilbert's Hotel, with its infinite rooms always able to fit one more guest, shows how nonsensical infinity can be when treated as ordinary quantity. In cosmology, an infinite universe, or infinite multiverse, creates problems that no clever trick can smooth over. If everything happens infinitely often, then probabilities dissolve. Every outcome, no matter how strange, occurs again and again. What does it mean to say something is likely if everything is guaranteed somewhere? Infinity does not expand knowledge. It erases its meaning, washing percentages away into an endless sea. These are not limits we can hope to stretch with better tools. They are embedded in the deep grammar of reality. They tell us that there are questions we cannot answer, not because we have not tried hard enough, but because the universe does not permit it. And yet these walls do not diminish the value of knowledge. In fact, they may heighten it. The orchard is sweetest not because it contains every apple, but because the apples we can reach are real, nourishing, and ours. The puzzle is intriguing not because it can be finished, but because of the pieces we do fit, each one giving a glimpse of the whole. The mirrors may never show what lies beyond the frame, but their reflections still shimmer with light. It is worth remembering, too, that acknowledging unmovable limits is itself a form of knowledge. To know where the horizon lies is to understand the shape of the world. To see where the resolution ends is to respect the texture of the canvas. We do not need to complete the puzzle to marvel at its beauty. So we arrive at a kind of quiet balance. Some limits are temporary, shifting with invention and imagination. Others are permanent, inscribed into the architecture of being. The art of knowledge lies in recognizing the difference. Where the wall is a door, we must push. Where the wall is a wall, we must pause, breathe, and accept. Gentle repetition helps anchor this truth. There are doors and there are locks. There are puzzles with missing pieces, mirrors with unreachable outsides, orchards where some apples always hang just beyond the ladder. These metaphors remind us that unknowing is not failure, but structure. Mystery is not the absence of knowledge, but the horizon against which it glows. In this way, the limits that cannot be moved do not close the story of curiosity. They frame it. They remind us that the universe is not a possession to be conquered, but a companion to be explored. And when we reach the walls we cannot cross, the act of touching them is itself an act of meaning, a recognition of where knowing meets silence. And so, after wandering across the wide terrains of thought, drifting through galaxies, peering into the strange symmetries of quantum worlds, walking through the quiet corridors of mathematics, and circling back into the folds of our own consciousness, we find ourselves standing at the tender edge of understanding. The great chest of knowledge has been opened. Its contents glittered in our hands for a while. Yet, when we look closer, we see its boundaries. Hinges that groan, edges that meet walls, and beyond them, a darkness that no light can cross. It might sound like a limitation, but it is in truth a relief. Knowing that the universe keeps some of its secrets means we are free from the burden of perfection. We're not here to conquer every mystery or to lock every truth in our grasp. We're here to notice, to wonder, to marvel at what can be seen, while accepting that some beauty lies in what cannot. Through the centuries, humanity has reached walls and learned to climb them. We have flown through air, looked across the abyss of time, and built instruments to touch the invisible. Some limits bent, others did not. There are the horizons that hide worlds from sight, the quantum fog that refuses to clear, the infinities that fold upon themselves, the walls of black holes and plank lengths that bar the way. These are not defeats. They are the delicate scaffolding of mystery, reminding us that the unknown is not an enemy but part of the design. And perhaps this is the gentlest truth. Meaning does not depend on completion. A flame does not need to burn forever to give warmth. A melody need not play every note to be remembered. A life need not know every answer to find peace. Knowledge too is beautiful in fragments, luminous in its incompleteness, alive in its imperfection. Imagine yourself once more beside a dark, still lake at night. The sky above is a tapestry of unreachable stars. Their reflections tremble on the water's surface, rippling softly with your breath. The lake does not own the stars, it only mirrors their light. That is what knowing feels like, not possession, but nearness. Not mastery, but resonance. The glow that reaches us is enough to remind us of the vastness beyond. And just as the lake is enough, so too is the journey. Every question asked, every glimpse of an answer, every line drawn in the sand, every thought that flickers like a match in the dark, they are ripples that carry us across the surface of wonder. We may never touch the farthest shore, but we keep moving, curiosity our quiet awe. That motion itself is the meaning. Here, at the edge of knowing, we may finally rest. The chest of knowledge remains partly closed, but its light spills through the cracks, enough to guide dreamers, enough to ignite generations of seekers, enough to cradle us in the quiet hum of the night. So rest now, traveller of thought. Let the unsolved become soft pillows beneath your head. Let the questions hum like distant lullabies. You do not have to hold the universe. You only have to drift within it. The cosmos continues, vast and tender, carrying you through its rhythm as you fall into sleep. In the stillness of night, knowledge does not disappear. It settles gently, like dust over the floor of time. Tomorrow curiosity will rise again, shining through you like morning light, urging you to lift the lid once more, to reach, to wonder, to listen. But for now, close your eyes. Let the world rest beside you. The universe is not silent, it murmurs. And tonight that murmur is a promise. You belong to its story. You're made of its questions. You live within its mystery. And that, in itself, is enough.